Here is the lecture for section 7.2, sampling proportions. In this lecture, we're going to be delving deeply, not just about sampling distributions, but in particular, the sampling distribution of sample proportions, or p-hat. We'll need to be able, by the end of the lecture, to find the mean and the standard deviation of the sampling distribution of the sample proportion. We should be able to determine whether or not it's appropriate to use a normal approximation to calculate probabilities. And then we should be able to do some calculations of those probabilities and then maybe use them to evaluate the quality of a claim about that. But to get you to have a sense of what's going on, what we're going to do is we're going to build a distribution of sampling proportion, or the sampling distribution of p-hat. And we're going to do so using this activity called the Reese's Pieces. Um, we are going to play around with this applet, following the directions. We're going to change the probability of the orange candy coming up to 0.45. Let me change that to 0.45. We're going to have 25 candies coming out of the machine. We'll take a sample and let's go ahead. Oh, we're going to change the statistic to being the proportion of orange, and we're going to be interested in what's going on as we get more and more p-hats, what's going on with the sampling distribution of p-hat. All right, so I think I got everything set up here. I'm going to go ahead, draw a sample. We see the machine doing its little business there. And so we got this one sample, and what happened? Um, well, it looks as though the p-hat value is 40%. 25 candies were sampled, 40% of them were orange. And we can see there that that one sample is that one little dot right there. That sample 40%. So far, we've got one sample. Its mean is 40%. The standard deviation, well, we don't have enough. We only have one value there, so we don't have enough to calculate a standard deviation. So we did that one sample, and indeed we got 0.400 as that as that p-hat value. All right. Now, that's only one sample. That's not nearly enough to think about in terms of the distribution of sample proportions. So what I'm going to do is I'm going to change the number of samples to uh, to 9. And so when I hit draw samples now, what's going to happen is I'm going to get 9 more samples, a total of 10 samples. And let's go ahead and do that, watching the canning machine do its bidding. So we get another sample, and every time we get a sample, we're going to end up getting an additional dot in this dot plot. Sample after sample, each one of them consisting of 25 candies, and then counting up what proportion of them were orange. Okay, let's see what we get. All right, the very last sample we took was 0.56, but we can see that there's all kinds of different values of p-hat that came out. And what we're seeing is that the mean of all those p-hats so far is 0.452. And I say, well, geez, 0.452, that's really close to 0.45. Are we surprised at that? Not at all. And the standard deviation of the all those different p-hat values was 0.071. So 10 samples, and we've got a mean that's pretty close to our population mean, a standard deviation. Now let's speed this up a little bit. Let's change this and let's do an additional 390 simulations. Now we're not going to watch the candy machine do each one. We're just going to say turn off um, turn off the animation, and then let's go ahead and draw the samples, and boop, there we have it. We have all of those now 400 different p-hat values in that. And how would we describe different elements of that estimated sampling distribution? Well, that shape looks approximately normal to me. Certainly, it's got a single mound in the middle. It goes off towards the tails. So I'll say the shape is approximately normal, right? The center, well, as we can see here, the center in the mean was listed as 0.447. Now, I need a good symbol for this. It's a mean, so I'll use mu, and it's the mean of the p-hats. So it looks like the mean of the p-hats, I'll use an approximately here, was approximately 447. Okay. And then the standard deviation, 102 with a period in front of it. Okay. And a good symbol for this would be the sigma of the p-hats, the standard deviation of the p-hats. And really, I should say approximately because this was done using a simulation. All right. That's a little bit of insight. Looks like it's normal. I got a number here that's really close, really close to this 0.45. And let's do this again. But this says, hey, let's take a look at it again. But instead of a sample size of 25, let's reset this machine. Let's have the sample size be 50. And let's go ahead and do 400 samples from that. Let's let that go. And then let's see if we can see any differences between these two. All right. What about shape? Well, the shape of that estimated sampling distribution still looks approximately normal. I wonder if that's going to be approximately normal all the time. The center, again, looking at the mean here, looks like it's still around 0.45. So these look the same for both 25 and for 50, right? And then what about the spread? What about the approximate standard deviation? Well, it's 0.6068. And that looks very much smaller than what we saw with a sample size of 25. Let's think about that for just a second. In the previous unit, we had mentioned that as sample size increases, we think the variability would decrease. And as measured by the standard deviation, we do indeed see a smaller standard deviation. All right. How about we make another change? What happens if we change the population proportion? No longer do we say that there are 45% orange candies. We're going to change it to 15% orange candies. Let's go ahead and let's do a draw of 25 candies 400 times. Remember, each dot being the outcome of one of those simulations, 400 total simulations. All right, what do we see? And again, we're going to do this when n is 25. In terms of shape, I don't think it's normal again. I think there's a slight skew right behavior that we can see. See how that little bit of tail there? It's not symmetric anymore. It's skew right. Well, what about the mean? What about the center? Well, I think, again, mu of p hat, the mean of the distribution of, looks like it's approximately 0.15. Oh, that looks as we expected because the population proportion was also 0.15. What about the standard deviation? What about the spread? Spread of p hat is approximately, in this case, 0.072. And again, pulling that number off of that graph there. Okay, so is that similar to what we saw before on the spread? when we had a sample size of 25? The answer is no, they're different. That's interesting, right? Again, now let's do it again, but let's do sample size of 50. I'm going to reset the machine. I'm going to change my sample size to 50. I'm going to do 400 simulations where we're drawing 50 candies apiece. And we're going to ask the same questions. What's the shape? I think this is approximately normal. I think I'm seeing that same symmetric on both sides. Center, as measured by the mean of those sample proportions, it looks to be about, 0.15 again. So that stayed the same, but this is different, isn't it? The shape is different. And then lastly, what about that spread? What about the standard deviation of p hat? We're seeing approximately 0.050. Well, that's like a third of the size of the standard deviation that we saw. So this is different. This is different from the 25. And again, we expected that because sample size got bigger. So the spread got smaller, the variability got smaller. But it's also different from what we did when we had a sample size of 50. So there seems to be a lot going on here. Let's see if we can summarize what we think we've seen. In terms of shape, I think it's safe to say that in some cases, it looks like it's approximately normal. In some cases, it's not. And it seems to depend both on the size n and the population proportion. The center seemed to always be the same as the population proportion. The mean of the sampling distribution of p hat always seems to be where the population proportion is. And then lastly, we did indeed see the sampling distribution's standard deviation get smaller as n got larger. It seems to depend also on the value of p because we didn't get the same standard deviation with when the population proportion was 50%, or sorry, 45%, as compared to when the population proportion was 15%. Let's see if we can connect this back to some things that we talked about earlier. And mostly the idea that the number of successes, x, divided by the sample size, n, gets us p hat. Well, that x, the number of successes, that's binomial. That's a binomial random variable as long as the population is substantially bigger than our sample size. Do we think, when we drew 25 candies, do we think there's at least 10 times, 250 candies out there? Sure. And if we do a sample size of 50, do we think there was at least 500 candies out there? Sure. So I think we meet all the criteria for a binomial. It's either ordered or it's not. Each draw is relatively independent. There's a set number of draws, n equal 25, n equal 50, and the probability of success is the same on each draw. All right. If that's the case for a binomial random variable, we know that the mean of the binomial random variable is n times p. We know that the standard deviation of a binomial random variable is the square root of n times p times 1 minus p. Now, if I do a linear transform, like we talked about in the previous chapter, by dividing everything by n, we are saying that p hat is x divided by n. Therefore, the mean of p hat is the mean of x over n. Well, what happens when I take 1 over n and I multiply it by the mean of that random variable x? Well, I just get p. Oh, that's good news. We have now proof that the mean of the sampling distribution of p hat is the same as the population proportion itself, making that confirmed that p hat is an unbiased estimator of p. Remember that definition of unbiased estimator? That the mean of the sampling distribution of p hat is equal to the parameter, the population proportion, that we would be trying to estimate. Great. Now, what about the standard deviation of p hat, which is the standard deviation of x divided by n? Well, if we start with that formula, dividing n by the standard deviation of the binomial random variable, and we bring the n inside, and that action squares it. This is all algebra 2 stuff. And then we know we have an n on the top and an n squared on the bottom. We can do some cancellation. We get the square root of p times 1 minus p over n. And that is our standard deviation for p hat. Let's take a quick look to see whether our simulations match that pretty well. We had said that from our simulation, we got 0.50 for the standard deviation. Using the formula, this would have been 0.15 times 0.85 divided by 50. And if I bring my calculator up, start a new document, here we go. I can ask, what is that square root of 0.15 times 0.85 divided by 50? 0.050. Well, is that right? Did I write that down wrong? Oh, I can see I entered it in wrong. Let me try that again. That's not 15. That's supposed to be 0.15. Let's try that again. 0.0505. And we had 0.050 something. So indeed, we can see that the simulation is really close to the theoretical value for that standard deviation. All the stuff that I've circled here, it's all in your formula sheet, but you would be really wise to memorize it. Let me say that one more time. You'd be wise to memorize that the mean of the distribution of sample proportions is the same as the population proportion itself. That the standard deviation of the distribution of sample proportions is equal to the square root of p 1 minus p over n. All right, so let's summarize it all. It says that if we are pulling a simple random sample of size little n out of a population whose size is capital N, and the proportion p of successes, then we can think of the mean of that sampling distribution being equal to p itself, the standard deviation of that sampling distribution of p hat being square root p 1 minus p over n, as long as the 10% condition is satisfied. Remember, the basics, the fundamentals of that formula we used was binomial. Binomial needs to be independent. So we need to be independent enough. We need our sample size to be smaller than 10%. And then lastly, what about the shape? Well, you could recall, maybe you recall that a binomial distribution was approximately normal okay? But only if n times p was greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, that we expected at least 10 successes and at least 10 failures, okay? In the case of p being equal to 0.15 and n being 25, well, 0.15 times 25, how many? Oh, we only expected 3.75 successes, and that value is less than 10. And that explains why in that combination, we saw a distribution that didn't look approximately normal. Whereas when p was 0.15 and n was 50, 0.15 times 50. Ooh, 7.5. 7.5 is not greater than, is less than 10. So this also would have made us suspect that this was also not normal. Let's go back and let's look at that one more time. I think it's still up in our applet. And that is that, yep, this is the 50 with 1.5. Do we see a little bit of skewness there? Maybe just a little bit, yeah. So maybe that's what they're saying. They're saying there, hey, we didn't get at least 10 successes, or we didn't expect 10 successes. Therefore, we're going to get a little bit of skewness there. All right, let's go ahead and look at this next set of check for understanding questions. Okay, it says about 75% of young adult internet users ages 18 to 29 watch online videos. Suppose that a sample survey conducted of 1,000 young adult internet users calculates the proportion p-hat of the sample who watched that online video. What is the mean of the sampling distribution of p-hat? Where our symbol is mu subscript p-hat, and we think that that's equal to p, and we were told that p was 0.75. Okay, do we have to check any conditions to say that's true? Nope. This is always true. All right, so find the standard deviation of the sampling distribution of p-hat. Check the 10% condition is met. And let me do this part first, and that is n times p, which was 1,000 times 0.75. That's 750. 750 is greater than or equal to 10. Oh, I'm sorry. I did that wrong. Please excuse me. This belongs down here. Let me try this again. 10% condition. That's the condition. Is n less than or equal to 1/10 big N? Do we think that 1,000 is less than 1/10 the population size of young adult users? Is it reasonable to think that there's at least 10,000 young adult internet users, let's say in America? And the answer is that's certainly true. Because that's true, then we're allowed to use the formula square root p1 minus p over n, or in this case, the square root of 0.75 times 0.25 over 1,000. And our calculator says that answer, see, control squared to get the square root, control division to get that fraction, 0.75 times 0.25 all over 1,000. And we get that standard deviation is 0.0137. Let's go 4 digits on those kinds of numbers. All right, question 3. Is the sampling distribution approximately normal? Well, we've already checked to see that we expect at least 10 successes. In fact, we expect about 750 successes. We have to see how many failures we expect. That looks to be about 250. Both of these statements are true, so we'll put little check marks on them. Therefore, the distribution, no, let's write this out more handily. The sampling distribution of p-hat is approximately normal. Great. Question. If the sample size was 9,000 as compared to 1,000, how would this change the sampling distribution of p-hat? Well, let's do this one by one. Would it change the mean? Well, no, the mean would be the same. It'd still be 7.5. So that stays the same. Would it change the shape? Well, the shape is determined by whether we expect at least 10 successes. And I'm thinking that 9,000 times 0.75, which is 6,750. Yep, that number is greater than 10. So we meet that condition. What about n times 1 minus p? 9,000 times 0.25. I think I can do this one in my head. I know that if it's not a success, it's a failure. So I think that's going to be 2,250. Let me just double check. 9,000 times 0.25. Yep. And that number is greater than 10. So this is still approximately normal. So same shape. All right. What about the last piece? What about the standard deviation? Well, the standard deviation of p hat, 0.75, 0.25, but this time over 1,000, sorry, over 9,000. So control square root, and we'll control division to get us fraction, 0.75 times 0.25 all over 9,000 gets us a standard deviation of 0.00456. How does that compare to the other standard deviation? The other standard deviation was a little over 1%. This is like less than 0.5%. That's a substantial decrease in the standard deviation. Are we surprised? No, we are not surprised that this is smaller because as sample size increases, the variability in the sampling distribution decreases. All right. Now, what can we do with all this information? Well, now that we know the mean, the standard deviation, and the shape of many of these sampling distributions of p-hats, we can use them to do normal calculations, normal probability calculations. So, for example, a polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend college within 50 miles of home. What is the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true value? Follow the four-step process. Four-step process means that we take a moment and we say what our question is. We'd like to find the probability of that a sample would have a p-hat value between 33 and 37%, within 2% of 35. All right? Our plan is that we're going to say that we know a bunch about this situation. For example, the sampling distribution of p-hat has a particular mean, and that mean is 0.35 because it's the same as the population mean. We know that the spread has a particular value because when we check the 10% condition, we know that n we know that our sample size is 15. 10 times our sample size, sorry, 1,500, is 15,000. And do we think that there's at least 15,000 first-year college students in the United States? And the answer is yes. So that's reasonable. Shape. Do we have enough evidence to suggest that the shape of the sampling distribution of p-hat is approximately normal? Well, n, 1,500 times p, 35%, is equal to 525. Nope, I put that over here, 525. And that 1500 times 1 minus P, which is 65%, should be 975. It is. All right. And both of those numbers are greater than or equal to 10. So I give myself a check mark, say that condition has been matched. So we know the distribution of P hat is normal, the center of 0.35, and a standard deviation. Oh, we forgot to calculate the standard deviation. Standard deviation of P hat for this situation is the square root of 0.35 times 0.65 over 1500. Square root of 0.35 times 0.65 all over 1500. And that is 0.2123. Oh, 123. Great. So if we know that this is true, now it says standardize. Let's do what they say. Let's calculate the z value for our two bounds. One bound is 0.33 minus 0.35, the mean, over the standard deviation, 0.123. So control division, 0.33 minus 0.35 all over 0.123. And I get something that 1.6, and it rounds to 3. And by the way, if I do this again, I get 0.37 minus 0.35 over 1.23. And we shouldn't be surprised that ends up being just the positive version of that. If I go to my tables, if I go to my probability tables, go to my z table, 1.6, negative 1.63. That looks to be about 0.516. Probability that z is between negative 1.63 and positive 1.63 is going to be something minus 0.516. The upper bound, we go back to the table. And you're thinking, boy, it's been a long time since we've used the table. I'm going to agree. And that's 0.9484. 0.9484. 0.9484 minus 0.516. And we get 0.8968. Okay. And you're like, why haven't we done that recently? Well, it's because we've been doing norm CDF, and we would have probably said lower bound 0.33, upper bound 0.37, where the mean is 0.35 and the standard deviation is 0.123. And let's just see if we get about the same answer. Menu, probability, distributions, norm CDF, 0.33, tab, 0.37, tab, mean of 0.35, and tab, and we said the standard deviation was 0.123. That number doesn't match at all, does it? Why is that? Did I pull the wrong numbers out of the table? 1.63, no, that looks good. upper, lower. Do I have the right standard deviation? Oh, I have the wrong standard deviation. Silly me. Okay, let's go back up to the on the calculator. You probably noticed it, and I didn't even notice it because that's supposed to be 0.35, making this standard deviation 0.0123. All right. And oh, and I even wrote down the wrong Z values too. Okay. I screwed up that Z calculation. Let me see if I can fix that. And that should be a 0 there. And I literally had the wrong number and I wrote the right number. I had the wrong number on the calculator, wrote the right number. Okay. So now that we've cleared that up, we'll go back to normal CDF. And I put a 0 in here. And boom. There's our 89%, just like we saw there. Conclusion. There is 89.6% probability that a sample proportion is within 2% of 35%. All right. And that concludes this lecture. Let's talk about what we learned. So first of all, when we're doing these processes, we often take simple random samples for some unknown parameter P. The sampling distribution describes how all those P hats would look over all possible samples of the same size from the same population. We know that P hat is an unbiased estimator of P, meaning that the mean of that sampling distribution is the same as the population proportion itself. The standard deviation can be found using this formula, but only if we meet the requirements of a binomial distribution that is independent. Remember, we say that as long as n is less than 1/10 big N, sample size is less than 1/10 of the population size, that we are independent enough. And so we check that independence condition to make sure that it's valid that we can use that formula, which was based on the binomial distribution. Remember, larger sample sizes lead to smaller standard deviations, less variability in the distribution of our statistic. When the sample size is large, then the shape of the sampling distribution of P hat is approximately normal. How large is large enough? Large enough that n times P is greater than or equal to 10, and n times 1 minus P is greater than or equal to 10. And that concludes our notes from section 7.2.